different method was always an interest for the researchers. And among different methods for detecting and characterizing those microorganisms or particles, I focus in this talk on impedance flow cytometry, which can give us a real-time analysis which has high sensitivity. It is label-free, so we don't need a fluorescent marker on our particles or organisms. And it gives us single cell level detection. It is minimally invasive, which is, again, a very good advantage when we want to work with the microorganisms. And it also enables us with the multiplex cell test. And using that method, we are aiming to find a fingerprint for detecting microorganisms, do dimensional and shape analysis, and do viability analysis for the microorganism. And at the end, combining this detection method with the sorting. But how does impedance flow cytometer works? Everything will be started with the preparation of the sample. When the sample is prepared, it will be injected using a syringe pump to a microfluidic chamber. This microfluidic chamber has 3 electrodes in the coplanar configuration, and these 3 electrodes will give us 2 sensing zones. And these electrodes will be connected to a lock-in amplifier and a current amplifier for the detection. When the particle passes through each sensing zone, it will change the impedance of that sensing area. And this change in the impedance can be read as the peak in the signal. And then later, analyzing and studying this peak in the signal can give us information about the dimension, about the shape, or other information that we want from the particle or from the microorganism. And at the end, we have the outlet of our system, and we collect our sample. But before I start to design and fabricate my system, I question myself that which dimensions should I use for my microchannel and for the positions of my electrode. Therefore, I started to model my system, first to understand the physics involved in the sensing, and then to define an optimization criterion, and then use that optimization criterion to find the best or the most optimum values for my system. I use the symmetry in the system, and everything in the modeling will be started with the double layer on top of our electrode. And after the current pass through the double layer effect, it goes through the electrolyte, which I modeled as a capacitor for the permittivity of the electrolyte, and resistant for the conductivity of the electrolyte. And then here is the most important part of the model, which is modeling of the cell or the bacteria. And we know that cells or bacteria, they have a membrane, and that membrane has some energy storing effect, and that energy storing effect can be modeled as a capacitor. And then we have the cytoplasm inside of that membrane, which can be modeled as a resistant. In the next step, we have the parasitic effect as a capacitor outside of the microchannel. We can also see the equivalent electrical circuit with different components of the sensing here. And since we have the AC measurement device, and since we have also capacitor component in our system, we can predict that our system has different behavior in different frequencies. Therefore, we started to study the behavior of the system in different frequencies. At the beginning, in very low frequency, the double layer is very dominant due to the high value of the double layer capacitant. And with increasing the frequency, we have this range that we are measuring the electrolyte. And there is a point with increasing the frequency that we can penetrate to the membrane. And here is the point that we can measure the membrane of the microorganism. With increasing more of the frequency, the membrane will be short-circuited, and then we are able to measure the cytoplasm. And with more increase in the frequency, in very high values of the frequency, the parasitic effect will be measurable. So here again, the equivalent circuit that you saw also in the previous slide. I wanted to use this model to find an optimization criterion. So I removed the particle from this equivalent circuit to have both the situation when the particle is inside of the microchannel and when the particle is moved from that sensing area. So having the contrast between the impedance of these two conditions will give us, can give us a optimization criterion, which I named it as a normalized impedance. And then I thought that what are the influential parameters on this normalized impedance, because I knew that with increasing this normalized impedance, I can also increase my sensitivity. So the first thing was the dimensions of the microchannel, width and height of the microchannel. I did a study and I saw that with, it was a little bit clear for me that with decreasing the height and width, so the dimension of the microchannel, my normalized impedance will be increased. And, but since I wanted my system to be universal and since I wanted to detect different ranges of the particle, here was not my stopping point to find optimal value. So I continued the study with the width of the electrode and the gap between my electrodes. And later in the next steps of the project, I will do the optimization for the conductivity of the electrolyte. So I used a FEM analysis using a COMSOL ACDC model to find my optimal values. So again, I started with the frequency study to find the frequency range that I can measure myself. And then I started my optimization with increasing the width of the electrode. We see that with increasing the width of the electrode, the normalized impedance will be also increased. But this increase in the normalized impedance at the beginning is much higher than at the end of the width, at the end of the increasing. And that is because at some point, the electrical field inside of the microchannel will be saturated. So the more increase in the width of the electrode doesn't bring that much advantage. And then I started to increase the gap between the electrode. And at the beginning, we see that with increasing the gap between the electrode, the normalized impedance will be also increased. And that is because when the gap between the electrodes are too short, the tunneling effect will happen and the short circuit will happen between these two near electrodes. And then when we have a very large gap between the electrodes, we see that the footprint of the electrolyte will be so high that the normalized impedance will be again decreased. So here we see that basically we have an optimum value for the width and gap of the electrodes. And then using this optimization method, I started to fabricate and design my microchannel and my microelectrode. So the microfabrication will start with spin coating of a thin layer of PDMS on a glass wafer. And then both glass wafer and the PDMS, they will be structured using a femtosecond laser ablation, which you can see as the first part here in this photo. And then the second part of my system will be fabricated using a normal photolithography process using gold and titanium as adhesion layer. And then these two separated layers will be sealed together using that thin PDMS layer in between. And all this sealed system will be mounted on a holder together with a PCB for my detection. So after optimization, after designing and fabricating my device, I started to do a proof of concept experiment. In this proof of concept experiment, I used a latex bead, which has a diameter of 3 micrometer and it's a spherical shape, and Puriesta megatherium bacteria with relatively similar dimension, which has a rod shape since it's bacteria. So I knew before the experiment that the latex bead is a solid particle and the bacteria has a membrane. So before doing the experiment, I was looking for a footprint of the membrane. I was looking for something which shows that the bacteria has a membrane and a solid particle doesn't have that membrane. So I looked into the phase shift in those peak of the signal that I showed you in the first slide. And I saw that the phase shift will be increased when I did the study between latex bit and the bacteria, which shows the polarization of the membrane in this frequency. Also, we can also see in this image that although the real part of the signal in both latex bit and the megatherium bacteria, they were similar to each other because they had relatively similar dimension, the imaginary part in the megatherium bacteria shows the higher value, which means again a footprint or this capacitive effect of the membrane in that microorganism. In addition to that, I did also a shape analysis. I knew that the latex bit is spherical, and I knew that the bacteria is a rod shape. So that means that the rod shape bacteria will spend more time inside of that sensing zone that I showed you in the previous slide. So here we see again that the width of the signal, which shows the duration of the existence of that particle in the sensing area, is more, in the bacteria, is more than the latex bit, which again shows that this shape analysis can be used for the detection. So as I told you, one of the aims was to find a fingerprint, which, as I showed you, the phase shift and also the shape analysis can be used as a fingerprint for detection. So as a summary, the aim of this research is fabrication of an optimized impedance flow cytometer to find a fingerprint for detection of bacteria. And so far, the optimization is done, and a microfluidic device together with the microelectrode is fabricated, and a proof of concept experiment is done, and we saw that the phase shift imaginary part and also the shape analysis can be used as a fingerprint to detect the bacteria with other normal non-biological particle. And in the next steps, I'm going to study the effect of the conductivity of the electrolyte on the optimization. And also, I would like to perform some experiment with the electrogenic gut microorganism. Thank you all for your attention.